Every ML researcher has hit this wall. You give a frontier model a long prompt, and it breaks. Not with an out-of-memory error, but by degrading into incoherence. Look at GPT-5. It has a theoretical context window of 272,000 tokens. At 8,000 tokens, it's near perfect. But push that to just 128,000 tokens, and performance drops below 60%. For tasks that require comparing every data point, quadratic semantic work, it collapses to near zero. This is context rot. It is the fundamental bottleneck preventing us from feeding entire code bases or million-token corpora into a model. But a new paper from MIT CSAIL proposes an elegant fix: recursive language models. The insight is deceptively simple. Stop trying to stuff the prompt into the context window. Instead, treat the prompt as an external environment variable. The LLM shouldn't ingest the text. It should interact with it through a read-eval-print loop, a REPL. Think of it this way. Current transformers try to read a library by photocopying every book into their short-term memory at once. An RLM just gets a library card. The prompt, P, is stored as a variable in the REPL. The model writes code to peek at slices, decompose the input, and, crucially, involve itself recursively. It's not a prompt engineering trick. It's a computational paradigm shift that yields unbounded input length and unbounded semantic work.
Let's trace algorithm 1. We initialize a REPL where the prompt P sits as a persistent variable. We inject a sub-RLM function. The LLM's actual context window? It starts empty, save for some metadata. Now we enter the loop. The LLM generates Python code. The REPL executes it. Here is the critical constraint. Only the metadata about the output, like its length or a snippet, goes back into the history. We never flood the context window with the full result. The model builds its answer in variables, iteration by iteration, until it sets a final variable. This decouples the input size from the context window size, allowing the model to perform OP-squared work via loops and recursion.
We don't hard-code these behaviors. They emerge naturally from the interface. First, read. The model writes regex patterns to filter thousands of documents, scanning for keywords without reading the full text. Second, decompose. It partitions the prompt, sometimes by line, sometimes by semantic chunks. Third, call. This is the power move. It loops over those chunks, launching a fresh RLM instance for each one, recursive depth. And fourth, answer. It doesn't try to auto-regressively generate a novel. It stitches the sub-answers together programmatically into a variable. It's constructing the output symbolically, not probabilistically.
To test this, the authors built a hierarchy of complexity. First, SNIA, finding a needle in a haystack. That's O1 work, pure retrieval. Then, BrowseComp Plus, multi-hop reasoning over 1,000 documents. Next, Oolong. You have to process nearly every entry. That's O of n. And finally, the torture test, Oolong pairs. You must compare every entry with every other entry. That is O of n squared complexity. This distinction is vital. Most long context models are just good retrievers. These benchmarks test if a model can actually compute over 11 million tokens of data.
The results are absolute. On BrowseComp Plus with 1,000 documents, the base GPT-5 model scores 0. It physically cannot fit the input. The RLM scores 91.3%. On O-long pairs, the quadratic task, the base model gets 0.1%. It's essentially random noise. The RLM hits 58%. Even without recursion, just using the REPL gives a boost. But look at the gap. Adding recursive subcalls drives a 14-point jump on the hardest tasks. Compare that to the summary agent baseline, which tries to compress chunks. It fails catastrophically at 0.1% on O-long pairs, because lossy compression deletes the specific details needed for pairwise comparison.
This scaling plot tells the whole story. As we scale from 10 documents to 1,000, the vanilla model holds up until it hits its 272K token limit. Then it crashes to 0. The RLM line? Flat. It holds 91.3% accuracy even while processing 11 million tokens. That is 2 orders of magnitude beyond the context window. And the cost? Surprisingly efficient. The median RLM run costs 99 cents. Feeding that same data directly into GPT-5 Mini would cost over $1.50. You are getting better performance for less money because the model learns to read only what it needs. Can a small model learn this recursive logic? Yes. The authors took Qwen3 Coder 480B, generated 2,250 trajectories, and filtered them down to just 1,000 high-quality training samples. They fine-tuned a tiny Qwen3 8B model for just 300 steps. That is only 48 H100 hours of compute. The result? The 8B model's performance jumped 28.3% on average. On Code QA, it went from 4% to 32%. This proves that recursive orchestration isn't some emergent property of massive intelligence. It's a learnable capability that can be distilled into small, efficient models.
Let's be precise about why other scaffolds fail. Vanilla prompting gives you O of 1 semantic work. You're bound by the window. RAD uses BM25 to fetch chunks, but it can't reason across them. The summary agent gives you O of N, but compression is lossy. You destroy the data you need for quadratic comparisons. Even Codact fails. It gives the model a REPL, but the model tries to print the file, flooding its own context window. You need all 3 pillars of the RLM: a symbolic handle for the prompt, symbolic output construction, and symbolic recursion. Remove any one of these, and the system collapses.
This paper reframes the role of the large language model. It is no longer just a text processor. It is an orchestrator of computation. It doesn't need to attend to every token. It needs to write programs that attend to the right tokens. The Qwen results suggest this behavior is distillable, meaning we could soon have small, specialized recursive agents running on consumer hardware. This shifts long-context AI from a modeling problem to a systems problem, a challenge of memory management, scheduling, and efficient recursion. The link to the paper and code is in the description.